Okay, so
Okay.
yeah, is it visible now? Screen.
Yes, yes, visible.
Okay,
Students can also answer whether they can hear properly. So
right. If they can hear us, I'm writing. Let's say, is it visible? Like whatever I'm writing.
Yes, sir.
Yes, sir, it's visible.
Okay, sir. So yeah, last class. Okay. Okay. I mean, anybody wants to share whatever you have learned last class? Hello. Am I audible?
Yes, sir.
Okay, so yeah, do you remember like whatever we have discussed last class? I mean,
Yes,
anything you want to
yes,
remind?
sir. We have learned expectation value of energies and and the uh, even potential.
Yeah. So how do you find the expectation value of energy? So you find this is the Hamiltonian. So you take
Yes, sir.
the expectation value. So how much do you get? How do you express it?
I think you can make full screen. I think your screen can be made full screen. I think.
Oh, is it not full screen? Let me try again. So is it fine now?
Yes, sir. It's fine.
Yeah, it's better.
Isn't it full screen?
It is not yet full screen. I think. No, I mean I am not able to see it as full screen.
Oh,
Others.
yeah. Is it full screen now? Hello.
I think it's okay. You can go ahead. It's no problem. I think.
Okay, sir. But in my system, it's full screen. I don't know what is the problem.
Okay. Okay.
Okay, sir. Uh, okay. So yeah.
Yes, sir. It's a summation of
Some
component square into energy, sir.
energy
Ci,
current. Okay.
yeah,
Yeah. What do you write?
Ci square
Okay. Ci square into.
into En or Ei.
Okay. Yeah. Okay. Right. So now, okay, we'll do something like this. Let's say you have the Hamiltonian, and I am writing our eigenkets to be En. So you'll get something like En into En. So this En are the eigenkets of Hamiltonian H, where En are the eigenenergies, eigenvalues. These are the energy eigenvalues. So okay, and for so any state psi that can be written as, okay, we'll come back to this, but before that, uh, we can write this Hamiltonian to be something like this: sum over n en ket en. So this is bracket notation. Like in this way, you can express your Hamiltonian, where we say that this Hamiltonian is diagonalized, or this is the eigenbasis En. So En are the eigenvalues of that Hamiltonian. So sorry, yeah. If we write our Hamiltonian like this, so then any state psi we can express in the eigenbasis of En. That is what we wrote, Cn En. These are the En are the eigenbasis. So Cn is the coefficients, and then you can express any state psi in this basis. Here there is something called completeness relation. This completeness relation tells that sum over
Sir, I didn't got. Sir, excuse me, sir.
yes,
I didn't got how you wrote this Hamiltonian in second line.
okay, this Hamiltonian,
Summation of n.
right?
Yes, sir. Means
Okay,
how you are using this outer product, sir.
okay, yeah. Okay, let's see. You have some Hamiltonian. You have some Hamiltonian matrix like this, and then what do you mean by diagonalizing the Hamiltonian? When we say diagonalization, in the sense you calculate,
All the eigenvalue will be in the
yeah,
diagonal positions.
you'll get the eigenvalues in this diagonal only. Other things are zero. So this Hamiltonian, whenever you write it in a sorry, we write it in a particular basis. So in every basis, the Hamiltonian is not diagonalized. So this Hamiltonian is diagonalized in a particular basis, that is called energy eigenbasis. So every operator that is diagonal in some basis, but it's not diagonal in every basis other than identity. So here this En I am able to write it in this way because these En are the Eigen Vectors for this Hamiltonian, right? So right, how you diagonalize the this Hamiltonian. Initially, like let's say you have some operator. Okay, if we take some example, let us say simply if I take let's say my Hamiltonian to be something like 1 0 0 minus 1. So what are the eigenvalues?
1 and minus 1, right?
Yeah, 1 and minus 1. But what are the eigenvectors?
Eigenvectors are 0, 1, and 1, 0, like 1, 0, and 0, 1.
Yeah, so eigenvectors are 1 0 and 0 1. Let's take another operator. I'm writing this h1, let's say h2. I'm writing 0 1 1 0. So what are the eigenvalues for this operator? Hello, can you calculate?
Yeah, sure.
Yeah, so let's if we calculate here, uh, let's say 0, 1, 1, 0. So I think it's simple, everyone can calculate. So it's like a minus lambda I, this state is equal to 0. So it's like 0 minus lambda 1, 1, 0 minus lambda.
It's plus minus 1.
Right. So you'll get plus minus 1. So from here, if you calculate, you'll get lambda square minus 1 equal to 0. That implies lambda is equal to plus minus 1. So what are the eigenvectors for this? What are the eigenvectors for this? If you find the eigenvectors, you'll get, it will be 1 over root 2, 1, 1, and 1 over root 2, 1 minus 1. So these are the eigenvectors for this matrix. Is it fine? You can easily calculate the eigenvectors. If you calculate, you'll see that these are the eigenvectors 1, 1, 1.
Yes, yes. Yes, like it is a sigma x, like Pauli spin
Right,
matrix.
right,
Okay.
right. So yeah, right. You got the correct thing. Sorry, there is someone waiting. Can someone admit? Sir? Okay. Yeah, so this is Pauli X. So this is Pauli G. This is Pauli X. So these eigenvalues are 1 minus 1, and eigenvectors are 1 over root 2, 1, 1, and 1 over root 2, 1 minus 1. So here the point I wanted to make is, see, for both the operators, the eigenvalues are same, but the eigenvectors are different. So when you say this Hamiltonian is diagonalized, so this H1 or sigma G is diagonalized in this basis, and sigma X is diagonalized in this basis. So this one, okay, let's say if I tell this state to be ket 0 and this state to be ket 1, and let's say this one to be tell some name, what to, let's say plus x, this is minus x. So if these are the eigenvectors, then this h1, we can write 1 into 0, 0 plus minus 1 into 1, 1.
Yes, sir.
Is it,
Got it, sir.
you got it right?
Yes, sir. Thank you.
Then what about this one? What you can write h2? It's like plus 1, like 1 into plus x plus x plus minus 1 into minus x minus x. So this is the same thing that I wrote here. This h is equal to sum over en, this k10, and this outer product of en. Is it clear now?
Yes, sir.
Okay. Yeah. So now, yeah. So okay, as you have already recognized that these are Pauli matrices, you can see that this plus x can be written as 0 plus 1 over 2, and minus x can be written as 0 minus 1 over 2, right?
Yes, yes, yes.
So Okay, so yeah, so this general formalism, we'll come back to this to do some problems in this polymatrix. But before that, let's do this common formalism, this Hamiltonian. So what I wrote, this was some digression. So I wrote H is equal to sum over n, En, outer product of En. So this is the Hamiltonian. And you know that our unitary, sorry, what is our unitary? This is exponential minus I h t over h bar, right? And if you see this unitary is that also commutes with this Hamiltonian. So because of that, you can express this unitary even in this basis of En. So what can you write? If I write this unitary u of t, this is the unitary, right? Exponential I minus IHT by h bar. This is our unitary, time evolution unitary governed by this Hamiltonian h. And h is, diagonalized in the basis of En. So this unitary you can write sum over n En into exponentially minus I En t by h bar. Uh, is it fine or it's confusing? Hello?
Yes, sir, it's fine, sir.
Yeah, right. So, like whenever you want to write some matrix, let's say go back here, let's say Aij, or let's say you want to write some matrix A, that you can always write like sum over Ij, Ij. So this is the in this bracket notation you can write any matrix like this, and it will be diagonalized in some basis, and that diagonal basis anyway you can write it in this special form that we are writing Hamiltonian. And if you notice that this unitary also commutes with this Hamiltonian, so because of that the eigenbasis of Hamiltonian is same as the eigenbasis of this unitary with eigenvalues, this exponential I minus I En t by h bar. And as you know that the unitary has the eigenvalues that are only phases, so the modulus of this eigenvalue will be always plus minus 1. So these are the unitaries. So now it's very simple how you can find the time evolution of the state.
Sir.
Yes.
So can you explain again?
Okay. Now, what I said, Hamiltonian, we can write it in this way. And this Hamiltonian, like Hamiltonian that commutes to its unitary. Because you see here only exponential of IHT over h bar is there. So there is no other operator than Hamiltonian. So when you express this exponential IHT, you'll see only powers of h. So that unitary always commutes with the Hamiltonian for this kind of time independent Hamiltonian. And having said that, you can express this unitary in this form where this En are the eigenkets and the eigenvalues are e power I En t over h bar. Right? Is it fine now? Hello?
No, sir. How does that form come?
Oh, this form. Okay. Do you understand this one? Hamiltonian commutes with unitary. Okay, let me write. So our unitary, what is unitary? Power minus I h t over h bar. now this is exponential of e power x. How do we express e power of x? E power of x is equal to 1 plus x plus
X
x
plus
square by 2 factorial
2
plus
factorial
x cube 3 factorial and so on. So that you can write sum over n x power n over n factorial. So similarly, this exponential ist over h bar, what I can write? Sum over, like let's say first one will be identity. Since this is operator, so one won't be there, identity plus h plus 1 over 2 factorial h square plus 1 over 3 factorial h cube plus all other higher order terms. So this is nothing but sum over h power n by n factorial. Is it fine?
Yes, sir.
So then when we find u and commutator of u and h, that is nothing but sum over n h power n by n factorial h. And you'll see that this will be 0 because this is powers of h. So this will commute. So always for this kind of time independent Hamiltonian, you'll get this commutator to be 0. And when they commute, they'll say they share a simultaneous eigenvalues. So the eigenvectors. So the eigenvectors of h and u are same. When a b commutator equal to 0, that implies a and b shares common set of eigenvectors, and that too they are complete. That means all the eigenvectors of A is you can write it as eigenvectors of B, something like that. So here H and U commute, so eigenvector of H is equal to the eigenvectors of U. So that is how I can write this exponential ist over h bar as in this form, where the eigenvalues are exponential I and t by h bar, because this h is there in the exponent, and when you write it in the diagonal form, this is nothing like this is like e power minus I e1 t by h bar, e power minus I e2 t by h bar, e power minus I e n t by h bar. So this is the matrix where these are the zeros, and this matrix is diagonalized in the basis of En. Is it clear now?
Yes, sir.
All right. So, oh, sorry, here I forgot t, and this will be t square. So h power n t power n by n factorial. Of course, I sorry, I also forgot h bar. Okay, these are just constants. So, yeah. So this is like h bar square is there, h bar cube is there, h bar is there. So t power by h power n, h bar power n. Now we can write the unitary in this form. So and then we know that any state psi, we can write it like sum over a n psi n. Sorry, a n e n. That is what we saw last time also. So you can write any state psi in the eigenbasis of En. Now when you want to find psi t, how do you get the psi t? You apply unitary of t on psi, so you'll get psi t. So that is nothing but what is u of t? U of t we have written this one. So u of t is nothing but sum over n en e power minus I e n t over h bar into psi, right? So that is nothing but sum over n is like e power minus I e n t over h bar into e n psi e n. So en, what is en psi? In outer product of en and psi. From here you'll get that psi, you'll get that en psi nothing but an. So you get here sum over n an e power minus I e n t over h bar to en. Is it clear?
Yes, sir.
Last class we did some problem like when the state will be orthogonal to the initial state and some problem like that. So the whatever you have done, that comes from here. So you can write the state in this basis and you can write the unitary in this basis. So that boils down to this kind of a form where this is the time evolution of the state. Now so similarly you can write the expectation value of h. What is the expectation value of h? Psi h psi. So psi is nothing but, if you see from this kind of equation, psi is sum over, so it's like en wait, yeah, what is our state psi here? An psi n. So I can write en star h is sum over okay, do you know about delta function, Kronecker delta?
Yes, sir.
Okay, so now our h I can write sum over, let's say sum over m ep sorry em. Similarly that this is our state psi, this is our Hamiltonian, and again our another state psi that we can write sum over p ep sorry this is ap. Now if you see, let's say there is one inner product here, so sum over m n p, so a n star into ap. So this inner product en with em will get delta mn. This inner product m and p will get delta mp. So from here you'll get like sum over n an mod square en. Right? Hello?
Yes, sir.
Yeah, so this is what expectation value of h we got last time. So now we'll see a similar question. Okay, let's do a simple question using our this Pauli matrices. So, all right. Yeah, so here if you see the inner product of psi of t and psi of 0, if I write psi of t and psi of 0, so this remains constant always, that doesn't change. How do you see that?
Because the phase gets cancelled.
Right. Sorry, here, I'm sorry, I wrote differently. This is like psi of t. This is same as psi of 0, psi of 0. So this inner product remains same throughout the time evolution. So this doesn't change. Like whatever separation you had in the beginning, so that separation remains always same. So you can see it like this one is nothing but u dagger, because psi of t is equal to u psi of 0. So this psi of t that you can write psi of 0 u dagger u psi of 0. So this u dagger u is nothing but identity, so you'll get psi of 0 psi of 0. So this is same state psi of psi. So this inner product remains conserved. So same thing happens if, let's say, two states, psi 1, let's say psi 1 of 0, and psi 2 of 0. So their inner product also remains same throughout. So you can write psi 1 of psi 0 of t into psi 2 of t, that is equal to psi 1 of 0 into psi 2 of 0. So this inner product remains same. This is because of, so here it is tell that the quantum mechanics or the unitarity of quantum mechanics preserves the inner product. So this distance between psi 1 and psi 2 and at any time that remains same. So if you are evolving them using the same Hamiltonian.
Sir,
Yes.
I have a doubt. This unitary, if
Yeah.
if it's unitary means Hermitian, then the eigenvalue will be real, and
Right.
means I'm not getting you are using unitary as an operator, and you are getting a new state. Means we have to get an eigenvalue and the same state, isn't that?
Yeah. So
My argument is that, sir.
yeah. So listen, unitary and Hermitian, they are different. For any Hermitian matrix, the eigenvalues are real, but for unitary matrix, eigenvalues are not real. It will be always a phase, e power I something. So eigenvalues, modulus of the eigenvalues of any unitary is plus minus 1. This H, this Hamiltonian, that is Hermitian, but this U is unitary. So you see the difference between Hermitian and unitary. See, this is our unitary. You see, here the eigenvalues are not real. E power I and t, this is not a real number, right?
Yes, sir. That means unitary is not an operator, sir.
No, unitary is operator. Operator is some general notation. So it can be unitary, it can be Hermitian, it can be anti-Hermitian, it can be anti-unitary. There are many things like that. So whenever you have some Hermitian, then okay, good point. So here there is a common like general statement. So it is said like that: if you have a Hermitian operator, then you can get a unitary matrix always. Let's say this is our operator H, always as unitary. Let's say I'll write U. So U is equal to e power I H. So this will be always unitary. So when H is Hermitian, this U will be unitary. How do you say so? Because you know that unitary means, for unitary, U into U dagger equal to identity, right? That is same as U dagger into U. So how do you confirm that? As we have seen, this unitary we can write e power, if this is IH, that we can write sum over n I power n by n factorial into h power n, right? This you can write like this unitary. Then what is U dagger? What is U dagger?
raised to minus h dagger.
Yeah, so we will get something like sum over n minus I power n by n factorial into h dagger power n. And as I said, h is Hermitian, so for Hermitian, h dagger is equal to h. That Satya sir has already told. If it is Hermitian, that means it is self-adjoint. So this what? Okay, right. So now what do I get here? This is e power. This you can write sum over n minus I power n by n factorial into h power n. So then what is u into u dagger? What will get sum over n I power n by n factorial into h power n into sum over m minus I power n, m by m factorial to h power n. Is it clear?
Yes, sir.
Yeah. So now what will you get? Sum over sorry. Yeah. So what will you get here? Let's say I'm taking the same index n because it is fine. So what will you get here? U into U dagger
It's one.
So 1.
Identity. So it's an operator. So you'll get it to be identity. So for any Hermitian, you get one unitary, and if there is some unitary, then you can get one Hermitian matrix out of that also in this way. So this is the conjecture. You can always write like this. Yeah. So okay. Yeah. What? Okay. What we are discussing? Yeah. The inner product remains conserved. That inner product doesn't change. Okay. So now. Yeah. Right. Okay. Is it fine till now?
Oh, yes, sir, it's
Then
okay.
we'll do some problems. Okay, we'll do some small problems. Let's say we have given one Hamilton. Sorry, we have given one Hamiltonian E into 0 0 minus 1 1 plus 0 1 1 0. Can anyone tell what is this matrix? How to write this in a matrix form?
Like we have to take a tensor product. Like
Tensor product of
means
what?
like K0 is like 1 0, like the
Yeah,
column matrix, and bra 0 is like a row matrix. So
right.
like we will actually not tensor product, but like we will have to
This is outer product.
outer product. Yes.
Yeah.
So
So what will you get?
just calculating this.
Yeah, yeah. That's the way. But mm, for any for any operator A that they can write some over I j I j. So if this is the matrix form, so this is nothing but A11, A12, A13, like that, A21, A22. So it goes something like this: AN1, AN2. So this goes like this. So this is like this IJ, this is ith, this is J. Sorry, I. Let's say this. Okay.
And it would be like three of the components will be E and one will be minus E.
Yeah,
Like,
1 2 like that. This is J. 1 2 something like this. So ijth element means first row and first column. So this 0 0 for this one, this Hamilton and H, this Hamilton H we can write. So let's say this is ket 0, this is ket 1, this is bra 0, this is bra 1. Now ket 0 into bra 0, so the first element is E over here. Similarly, ket 1 into bra 1, so this is last element, this is minus E over here. So similarly, ket 0 into bra 1, so this ket 0 into bra 1, this is E, this is E. So is it fine now? Whenever you do that outer product multiplication, you'll get the same thing. So this is the way we write it in a outer product form for any matrix. Is it fine?
Yes, sir.
And if you just realize this is nothing but I can write it like E0 0 minus E plus 0 E0, right? I can write in this way. Then this E, if I take it out, this is nothing but 1 0 0 minus 1 plus E into 0 1 1 0. Is it clear?
Yes, sir.
So this is nothing but again sigma x into sigma x plus into this is, sorry, this is sigma g, this is sigma x. So this is like E into sigma g plus sigma x, right? Is it clear?
Yes, sir.
Yeah, and previously we have already seen that the let's say, so here I just want to write sigma g is 0 0 plus, sorry, 0 0 minus 1 1. So similarly sigma x is equal to 1 0 plus 0 1. Now we have to find the eigenvalues of this edge. We have to find the eigenvalues of this Hamiltonian edge. Yeah, as you know, like given this matrix, you can always find the eigenvalues and eigenvectors by doing the usual way of calculating eigenvalues and eigenvectors. But here we'll learn one technique so that we can find the eigenvalues of this kind of matrix, like for a different, for many such matrices, we can use this to find the eigenvalues and eigenvectors other than calculating each time. So here, as I said, here the eigenvalues are plus minus 1 and sigma x also eigenvalues are plus minus 1. And but for sigma x, if we, where do we write sigma x? Yeah, we wrote that plus x is 0 plus 1 over root 2, minus x is 0 minus 1 over root 2, right? So if you see, you have the sigma x. If you write operate it on 0, what will you get?
1.
Right. So how do we get it? This is like 1 0 plus 0 1 acting on 0. So this is this second term will inner product with like 1 0 0 plus 0 1 0. So the second term goes to 0 and this get 0 into get 0, this is 1. So this is nothing but get 1. So similarly, we'll get sigma x over 1 is equal to get
0.
0. And now, so having said that, this it is like sigma x changes from 0 to 1 and 1 to 0. But if I add them up 0 and 1, then it will remain same. Like sigma x 0 plus 1, what will you get? 0 will go to 1, 1 will go to 0. So it's same thing, right? So that is why this 0 plus 1 is an eigenstate of sigma x. And just to normalize, we are dividing it by root 2. Now, this Hamiltonian h is something like sigma g plus sigma x. So we have to find the eigenvectors of sigma g plus sigma x rather than only sigma x or sigma g. Okay, now as we have seen, sigma g on ket 0, what will you get? sigma g is like ket 0 has eigenvalue +1 and ket 1 has eigenvalue -1. So these are two eigenvectors for sigma g. Now sigma x changes ket 0 to ket 1 and ket 1 to ket 0. So similarly, this is, let's say, plus x. So similarly, sigma. So now we'll see that sigma g, if I act on 0 plus 1 by root 2, what I'll get? What I'll get here? Sigma g on 0 is ket 0. Sigma g on 1 is
-1.
-1. So this one will get 0 minus 0 minus 1 by root 2. So this is nothing but minus x. So sigma g on plus x, that gives us minus x, and vice versa. So sigma g on minus x will give me plus x. Is this calculation confusing? Hello?
No, sir, it's okay.
Okay. Yeah. So now, okay, now just remember sigma x changes from 1 to 0 and 0 to 1. So similarly, sigma g changes from plus x to minus x and minus x to plus x. But if I have some state like I have the Hamiltonian sigma x plus sigma g, and I'll act on 0 plus x, what I'll get? What will you get from this one? Sigma x will change from 0 to 1. Sigma g will give it 1. So okay, so this one we can write sigma x plus sigma g on 0 plus sigma x plus sigma g on plus x. So sigma x on 0 will give us 1. Sigma g on 0 will give us 0. Right? Hello?
Yes, sir.
So now sigma x on plus x will get plus x. Sigma g on plus x will give us minus x. So what is the state finally? This is 0 plus 1. This is, what is plus x plus minus x?
X plus z plus x. X.
So like 0 plus 1 over root 2 and 0 minus 1 over root 2. Isn't it? What do you get? What is plus x? 0 plus 1 over root 2 plus 0 minus 1 over root 2. So what is it? 0 plus 1. This gives us plus 0 by 0 plus 1 over root 2. Okay, let's say, yeah, I am dividing this whole state by root 2. So this is just to normalize. I forgot to normalize in the beginning. So we'll get this one 1 over root 2. So here 1 over root 2 is there. So this ket 1 plus 1 minus 1 will get cancelled. We'll get this one is like 1 over root 2. This is ket 0. This is 1 over root 2. 1 over root 2 will be root 2 into 1 over root 2 again is there. So this is nothing but 0 plus 1 over root 2 is plus x, and this is root 2 will get cancelled. This is ket 0. So this is again an eigenstate of this sigma x plus sigma g, and or if you observe this root 2 over here, so this 0 plus x is an eigenstate of sigma x plus sigma g over root 2. Is it clear? Hello? Hello? Am I audible?
Yeah, yes.
Yeah. So is it confusing?
So it's little lengthy. No?
Huh? Sorry?
Isn't that lengthy? So,
Yeah, I just wanted to show you these things.
yeah.
So once you understand this one, so my point was, you just if you just stare at this state 0 plus x, then you'll see that this is one eigenstate of sigma x plus sigma g by 2, sigma g over root 2. So once you understand this calculation is it's not required for you. Once you do this just once in lifetime, then you are done. So then when you see this kind of one matrix, and you don't need to go and calculate the eigenvalues and eigenvectors explicitly. Now you can simply write what can be the eigenvector. So see this Hamiltonian sigma, I mean E is there, this Hamiltonian. So for now, our Hamiltonian is E into sigma x plus sigma g. So that I can write E over root 2, or sorry, that I can write square root of 2 into E into sigma x plus sigma g by root 2. And now you know these eigenvectors. So eigenvectors for this Hamiltonian will be, so eigenvalues will be root 2e and minus root 2e, and these are the eigenvalues. So similarly, eigenvectors will get 0 plus x, 0 plus x, and 0 minus, sorry, 1 plus minus x. So these are the eigenvectors. You just normalize properly. So is it clear now?
Yes, sir. Yeah.
So here I just wanted you to do this calculation just once in lifetime. Just you just need to understand that there is a very nice structure for this kind of operators, Pauli operators, and there is a very nice relationship among their eigenstates. So once you understand that, then it is very easy. You don't need to do all these calculations. So you can see the next problem that we are going to do. Let's say this is So I just wanted to do this calculation, but this kind of problems are coming many times in your exams, like entrance exams. So here one question is given. Your Hamiltonian is A, B, B, A. So can anyone tell what will be the eigenvectors and eigenvalues? Any guess? What is this matrix? Can we write it some similar form like we wrote before?
Like A identity matrix plus B
Right. A
sigma
into identity plus B into sigma
sigma
x.
H.
So what are the eigenvalues for this? What are the eigenvalues for this?
Yeah, S R minus B.
Yeah, right. So what are the eigenvectors? What are the eigenvectors? See, any vector is an eigenvector of identity, right? That doesn't change. Now, if now the problem is for sigma x. So all the eigenvectors of sigma x are also eigenvectors of identity. So your eigenvectors are, so eigenvalues are a plus minus b. Oh, let me write individually a plus b and a minus b. Similarly, eigenvectors are plus x and minus x, isn't it? Hello? Hello? Yeah. So these are the eigenvectors, right? Is it fine? Because identity anyway doesn't change, only sigma x. So sigma x, these are the eigenvectors. So
Yeah,
it remains same.
got it.
Right. So now there is another such question, I think, that appeared in jest, if I remember correctly. So that also depends on similar calculation. So the Hamiltonian is given h is equal to h bar omega by 2 1 1 1 minus 1. Now what is this matrix? Can we write in the similar form? Hello?
This is a Hadamard operator, I think.
Right. Okay, are you familiar with this quantum computing thing?
Yes, little bit.
Okay, yeah. What about others? Okay, don't worry for Hadamard. Now, just whatever calculation we did before, you tell, can you write it some similar form like this? This is nothing but h bar omega by 2. This is sigma g plus sigma x again. Now, what are the eigenvalues? So there are four. So there are four options. Option A is cos pi by 4, cos pi by 4. Option B, cos pi by 8, cos pi by 8. Option C, cos pi by 2, sin pi by 2. D, cos pi by 6 and sin pi by 6. Yeah, so how to solve? What will be the answer? Any guess? Or can you use some knowledge that we just learned? Hello? If you just realize, as we said, like this is sigma x plus sigma g. So this is something like this. This is the Hamiltonian E into sigma x plus sigma g. So as I said, the eigenvectors are this 0 plus plus x and 0 plus minus 3, 1 plus minus x. So if you see the first one, let's say 0 plus plus x. What is this state? This is 1 0 plus plus x is nothing but 1 over root 2, 1 minus 1, right? If I add these two, what I'll get? What will you get? 0 plus plus x. This is 1 plus 1 by root 2. Oh, sorry. So this is 1 plus 1 by root 2, and this one minus 1 by root 2, right?
I think that will be 1, no? Like plus x is like 1 by root 2, 1, 1. No? Minus 1 will be the minus
Right,
x.
right. Sorry. Correct. You are correct. This is plus 1. It's not minus 1. Now we'll see. You'll see that this will be the eigenstate, and we'll see. And one of these four options will be the answer. If you see the if you see uh, this this one, let's say cos pi by 8 and cos, this cos sorry uh, cos pi by 8 and sin pi by 8. Yeah, so 0 plus right. So let's say this option cos pi by 8 and sin pi by 8. This one is nothing but if I uh, multiply sorry okay now we are already 9:47. Let's solve some other problem. Okay, you take it as homework and you use the technique, like then you'll see that the answer will be this cos pi by 8 and sin pi by 8. It is because out of this form you are seeing. So my point was, whenever you are seeing the Hamiltonian is some form of using these Pauli matrices like sigma x, sigma y, sigma g, and identity, then there is a very nice structure for the eigenvalues as well as the eigenvectors. So using that, you can easily find the eigenvalues and eigenvectors before you don't need to do any calculation all the time. So simply use that technique and then you will be able to find the eigenvalues and eigenvectors. Like we just see just three examples here, but you'll get many such examples. I mean, many such questions in exams. Uh, yeah. Okay. So yeah. So Is it fine till now? Whatever calculation we have done.
Yes, sir.
Yes, sir.
Okay. So, is it difficult or is it difficult?
No, sir. It's interesting.
Okay, then that's good. Uh, Let me see if we can solve. Okay, then let's do some more problems using inner product. Let's say this is 3, 4. I don't remember the number. But okay, you are given one state psi that is nothing but 1 over root 2, 0 plus 1 at time t is equal to 0. What time the state will be minus psi. So at what time psi of t, that will be minus of psi, where your Hamiltonian whatever is given, h of 0 is 0 and h of 1 is 1. Sorry, h of 1 is minus 1 into, so like minus 1. So this is the question. You have the state 0 plus 1 over root 2. You have to find at what time your state will be minus psi. So, right. So psi of 0 is equal to 1 over root 2, 0 plus 1. So psi of t is nothing but psi of t is nothing but 1 over root 2 e power minus I e1 t by h bar to 0 plus e power minus I e2 t by h bar to 1. Right. So this will be 1 over 2. Okay, e1 is plus 1 and e2 is minus 1. So e power minus I t by h bar plus e power minus I, this is plus I t by h bar, gate 0, this is gate 1. So now tell me at what time it will be minus, there will be minus sign outside. So if I take it by h bar common, so say 1 over 2 e power minus I t by h bar. So you'll get
Pi
the,
h cross. This is pi h cross.
right. So this is e power 2 t by h bar 1. So our state psi of t will be minus psi. So for psi of t to be minus psi, what do you want? This one e power. So for this one you want e power I t by h bar, that is equal to minus 1. So this gives us t is equal to pi h bar. And you will see when t is equal to pi h bar, this will be nothing but 1. So your state is going from psi of 0 to minus psi of 0. So, but if you see still this psi of t, now if you see this psi of t, the inner product of psi of t and psi of 0, what is it? -1. But the modulus square will be 1 again. So there is just the overall phase is changed, but the state remains same. See, the form of state psi and psi of t, they both are same. There is just a minus sign outside. That is called overall phase. In quantum mechanics, that you can always neglect. I mean, this overall phase can be neglected, but the relative phase cannot be neglected. Relative phase in the sense here this exponential it by h bar is there. So this factor you cannot neglect, but this first one you can neglect always. Yeah, so that means there is some, you have some freedom in choosing the overall phase. Yeah. So, uh, for like, when do we stop actually? How much time do we have? Hello, sir.
You can stop at 10 if if students do not want any more extension. You can stop at 10.
Okay. Okay. So okay, so it's already 55. Okay, let me just then write one or two questions. You can try at your home if we don't have time to solve here. Mm, okay, so say 3 or 4, whatever. It's given let psi 0 be an eigenstate of sigma x if our Hamiltonian H is equal to sigma g, then what is the minimum time when psi of t becomes an eigenstate of sigma y. So similarly, you can find the eigenstates of sigma y where the eigenvalues are again plus minus 1. So these questions I got it from previous year entrance, like CSIR, GATE and JEST. So what else? Yeah, one more question. You try to solve these questions. These are just based on the same concept. The Hamiltonian operator for a two-level quantum system is H equal to E1 0 0 E2 if the state of the system at t equal to 0 is psi of 0 1 over 2 1 1. If this is eigenstate of sigma x, then find psi of 0 psi of t mod square at a later time. That means what is the probability that the state remains in the initial state at a later time? So there are four options. One is 1 over 2 1 plus e power minus e1 minus e2 t by h bar b 1 over 2 1 minus e power minus e1 minus e2 t by h bar 1 over 2 1 plus cosine e1 minus e2 t by h bar d 1 over 2 1 minus cosine e1 minus e2 t by h bar. Yeah, so right. So yeah, so I just gave two questions. So these are only from previous year questions. You can find it. Yeah. So try to solve them. Today I just wanted to use just one concept. So I wanted to scan through all the questions, like the different questions we see using the same concept. So here we used Pauli matrices in the outer product form of any matrix, any operator like Hamish-Yar or hereditary. Then how do we express the expectation value, time evolved states, and so on. So is that fine?
Sir, can you suggest books to explore these properties of uh, this matrix,
Explore what?
this matrix?
Uh, uh, you'll not find any particular book mentioning all these things. I mean, you'll get sigma x. I mean, Pauli matrices you can get from any quantum mechanics books. But yeah, this calculation is not difficult. You just need to realize that uh, uh, there is a very nice structure. I mean, these things you'll get from any quantum computing book. So, but I am not I'm not telling all those words now. Just you don't need to worry for that. But you can do your own calculation, and this kind of calculation you can do always. It's not that difficult. So, if you have any problem, then let me know. Yeah.
The first question is the answer pi h cross by 2e.
Pi h cross by 2e. Which one?
The exercise problems.
Uh, okay, I don't remember the answer. You can
Okay.
take it.
Okay.
Yeah, 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 good. If you have solved. and you can help your friends also. So anything else? Any other comments or questions? So yeah. So shall we stop then?
Yeah, if no more questions are there, we can conclude. So thank you, Avinash, for spending so much time and solving so many problems. I think those are problems which are generally appearing for this type of exams. So it must be definitely very useful for the students. So thank you once again. Good night to all.
Yeah.
I think
Thank you, sir.
Sarana Kumar, Sarana Babu, you can stop recording.
Yeah, sure.